Hello, everybody. It is October 2021, and I thought it might be interesting for I to go through your fantastic questions on this course, Introduction to Database Engineering. You ask great questions, and kind of go through some of them that I gonna picked out, and then answer them in details. I try as much as possible to go through these questions and answer them. You guys ask fantastic questions, but I thought some of these questions it's very hard to answer in text, so it might be interesting to make a new lecture called Q&A and answer some of these questions in details. And I'm gonna, if you like these kind of lectures, let me know in the comment discussions. I guess you can have discussions in this lecture. Let me know if you want more, and maybe I'll gonna do it in a couple of months. How about we jump into it and see, try to answer some of these questions. So here's a question from Konstantinos. I hope I pronounced your name right. On the Getting Started with Indexing lecture on our Introduction to Database Engineering course. Getting different results with Explain Analyze. Hi Hussein, and thank you for the direct and comprehensive explanation you get every time. You're welcome. Running Explain Analyze using the exact same syntax with your two queries, I get different results. For the first, Explain Analyze select ID from employees where ID equal to 1000. I get a value of one heap fetches. For the later, I get none effectively, right? And then so they are effectively saying that I'm getting different results with every time I execute. Not the results. I get I get different timings when I execute this query twice. And let's explain a little bit here. What do we mean by heap fetches first? So when you execute a query, and specifically in Postgres, right, and that query goes through a path that is exclusively searching the index, which is index only scan. I talked about that in one of the lectures, index only scans. That means that it should only go to the index structure, right? Because we know that there are two structures. There is the heap with entire table worth of data, and there is another data structure called the index that has subset and pointers to the heap with the actual content. So if you're only doing an index only scan, you should only be looking into this structure, which is the index structure, right? Most queries that are index scans, normal scans, they go to the index, find what they want, and jump exactly to the page or the block in the table that has the data and pull it up, right? If you don't have an index, you have to scan the heap for the entire table, right? That's how basic indexing works. Heap fetches tells us that, yeah, I did an index only scan, but I had to go to the heap to do that. So this is kind of contradictory, because hey, if all the results is an index, why are you jumping into the heap? Postgres keeps these things called hints that tells you if a row is deleted, updated, or modified. So you see, when I delete, for example, a row in Postgres, or an insert, or even update a row, we create a new version of this row, because Postgres is an MVCC designed multi-version concurrency control, which means that we also update the index to update the entry, all right? That points to our tuple, right? Because the index also points to the table. Because you touch the row, we have to update the index to point to the new version, right? But we also keep the old version, because some other transactions are also reading, right, the old row, right? Because a running transaction need to make sure that the row is running and alive as a result. So because of this, all of a sudden now transactions need to make sure that is the row I'm looking at deleted or updated, or is it alive? To answer this question, is it alive? That bits, is it alive? Can I see it? is these kind of bits, the hint bits, are stored in the heap, and as a result you see these jumps. How do you get rid of these jumps? Well, two solutions. If you have long running transactions, then you will definitely see these jumps, because these jumps means that there are transactions that are very old, very long running, and they are reading old data that we cannot get rid of. That means, hey, from time to time, I'm gonna have to jump to the heap to check if this row is visible or not. But most of the time, if you don't have any running transactions, that means you can freely clean up these old rows, and we can freely avoid going to the heap to see if this row is alive or not. Run vacuum. I talked about vacuum and analyze and all this stuff in many lectures in this course, right? So if you run vacuum after all the updates, then you should get consistent results. As of the timing, right, they did mention that the timing is like 0.0047 millisecond versus 0.17 milliseconds. This is expected because the timing, you only have to worry about times if it's more than, I don't know, 10 milliseconds, right? 12 milliseconds, right? 6 milliseconds. But if it's less than a millisecond, there is so many variables with the hardware, you know, then you're getting into really low level stuff, and there's really no worth going through, right? If you're seeing 100 millisecond, 200, that's where you actually optimize. 0.1, 0.2, it's really non-deterministic. It depends on the CPU, depends on the hardware, depends on there's other processes running with Postgres. Your machine probably having multiple processes that is hogging your CPU. All right, so that's kind of answers this question. Let's pick another one. So this is another interesting question from Ihab Ahmed on the acid by practice examples lecture. Redis durability versus persistence. Hi, Sen. In minute 20, you said that Redis doesn't offer durability because, of course, it is in memory database, lives in RAM. If electricity goes down, data is lost. And also you said, but it has persistence. I need to know, what do you mean by that? And I want to understand your point. What is the difference between durability and persistence? They are effectively very, very similar, right? I might have confused you in that lecture, but let's try to kind of clarify this. So we're going to come to Redis, but let's explain the concept of persistence. To persist is to write to a specific location and have it there, right? So like if you write to a disk, it's persisted to disk, right? And then that means if you turn off the electricity and you turn it back on, the charge will still be there, whether you're using magnetic for a hard drive or charge in case of SSD. The data is there. That's called persistence. Now durability is a term that database uses, and the idea of, if I write, and if I said I started a transaction, I did a bunch of queries and I wrote few things, insert, update, and then I said commit, my transaction is durable if after the commit I tell you it succeeded, if after that, after a millisecond of you telling me that the transaction committed successfully, I can turn the database off completely. I can unplug the computer and then plug it back in and start the database, and the data should be there. Now the durability has to use persistence in order to obviously have the data on, right? And that's basically what it is. And now Redis is durable, right? But it depends on the type of durability option that you pick. And I don't believe I talked about this in detail, but here is free lecture for you guys. The idea of Redis has, I think, 3 formats effectively, right? There is the snapshot format, where asynchronously when you issue writes, these writes actually in Redis goes to memory first, and they will commit immediately, and they say, here, the write was successful because it was successful writing to the RAM, to the memory, right? Doesn't have, I say RAM, but memory is vast, right? Because could be virtual memory, right? Could be memory on disk. That's kind of memory, right? It's a temporal thing. RAM is the random access memory, the slot, the DIMMs, right? And when I write that, you get back commit successfully, but in that case, if you lose power, you lost your data. But Redis, what they do with the snapshot is, after a second or two, they take the entire memory and they flush it to disk. They actually persist it to disk. So it is only true that you lose your data exactly after that second, right? If the asynchronous process fails to write to disk and you lose power, then Redis will lose your data. But if you write, right, your transaction succeeded to writing to the RAM, and then the Redis asynchronous process kicks in and then snapshot the RAM to disk, and then it failed, then no, Redis is actually persistent and durable because, hey, it didn't lose your data. If it happened in that X amount of seconds and you can configure it, then you will lose your data. So yeah, it is durable, but there is an option that you can lose it. Now you can, this is the fastest write option. There are many other options in Redis that has stronger durability, because that was like a weaker durability, right? The stronger durability option in Redis is called AOF, append only file. I think I talked about it in the answer here as well. So the idea here is as you as you commit your transaction, we write it to the RAM, and also we write it to an append only file. Call it this redo log. Some people call it the wall, and in traditional relational databases we call it the wall, the write ahead log. And only when that succeeds, writing to the wall, which is the journal, which is on disk, then we actually say succeed. And this is effectively a log of the metadata entries itself, the actual description of the data, right? Includes the data as well, but doesn't have the full data structure of that data. Does that make sense? Like if you're writing into an index, right, the index itself is complex, right? But so the log will have an entry said write X to the index blah, right? So this is always compact, but writing to the actual indexes has the B trees, and you have to update many locations and stuff like that, right? So it's not one-to-one always. So that's the append only file in Redis has a stronger durability, and it's one-to-one, exactly identical to the relational database. So yeah, Redis is actually strongly durable if you choose that option, but it's gonna be slow in writes, because now you're writing to disk with every transaction, right? That's why Redis is only fast, because it's writing to memory, right? But there is always a choice. If you choose snapshot, you can choose both, I believe, AOF and snapshot as well, to get the best of the world. You choose snapshot, your writes are fast, but you might lose your data. If that happens, which is very rare that it can happen. If you're willing to take this chance, you can. Or you can have your writes being slow, but you have higher durability. The option is yours. That's why I like this choice in Redis. You don't have this choice in other Postgres or MySQL. I don't give you this durability choice. Let's go to the next question. So this is another question from Kanaru, shared on the shared versus exclusive lock lecture. The life cycle of a lock. In a transaction, if we update a row during updation, the row acquires an exclusive lock. Does it have an exclusive lock until the commit to the transaction? So the question is, what is the life cycle of a lock, right? So this difference from one database to another, but the idea is if I update one row, right, then that row is locked exclusively, assuming the database supports row level locking. Not all databases supports that. Some databases actually, when you want to lock one row, it locks the entire table because it says, hey, it's easier, it's cheaper to lock the entire table instead of locking one row. Because assume you update 1,000 rows. Do you maintain 1,000 locks? Yeah, that's what most databases do. SQL Server does that actually. Postgres does it differently. It maintains the lock in the table itself, right? Oracle does it different. Every database does it differently. But yeah, locks are expensive. So as you update, you maintain a lock. And when the transaction rolls back or commit, we release that lock. And the reason we obtain an exclusive lock on the row itself when we update it, so that nobody else actually tries to change it, because we don't want the transaction to change it. Sometimes I don't want other transaction to even read it, right? Read this version of the row, right? The word exclusive here is a little bit harsh. Exclusive means don't even allow reading it, right? This depends on the type of database. Again, some databases prevents you from updating it but allows you to read it, right? Some databases doesn't even have this concept, like Postgres. It has multiple versions. Hey, I'm updating this row, I created a new version and locked it. The old one is free to be read, right? You can still read it. So once you effectively roll back or commit the transaction, this lock is gone, right? Lock management is very, very expensive effectively. So yeah, that's in a nutshell the life cycle of a lock effectively, but there are many, many types of lock. Hope that answers that question. So let's answer this final question. Index scan versus index only scans. Krishna asks, what exactly is the difference between creating an index on columns directly versus including non-key columns, right? So they're asking the difference between, hey, what if I create two indexes here? I create index ID on the ID field and I create another index on the name field. So I have two indexes versus I create one index on the ID field and I include the name. There's a huge difference between them. First of all, this, you have two indexes, so you have two data structures, so you have two B trees, right? So twice the amount of, not really different storage, but twice the amount of data structures, right? And while the second is you creating one index and that index is keyed on the ID, but you are including with each entry the name, the corresponding name value, not to search for, but to include it. So that means if you search by the ID, the B3, the index will be used to search on the ID, and for free, when you find the ID, you can get the name for free without getting to the heap, to the table itself to fetch the name column, right? But if you search by the name column, this will not hit the index because the name column is not indexed. On the first example that you showed here, when you search by the name, yeah, there is an index and you can search by the name, right? It's a little bit of a different thing. And there's another way where you have a composite, all right, index where you have one index with two values where you can search by the ID and you can search by the ID and the name, but you cannot search by the name only as well because the name is on the right side of the composite key. I talked about that in another lecture. All right, guys, let's end it here. They're just answering 4 questions. It took us a long time. Let me know if you enjoy these kind of Q&A. I'm going to see you in the next one. Enjoy the course. Goodbye.